Fourier series. So for the upcoming tutorials you're going to have today or on Monday, we could be working away on there's the final set of exercises in the Laplace transforms chapter, exercises 2.4. So those are on differential equations featuring the Heaviside step function and the Dirac delta function, yeah? And also the previous set of exercises, exercises 2.3, they're preliminary exercises on working with the Heaviside step function and using it to express functions that are defined on a case-by-case basis on different cases for the argument. So there's plenty of stuff to be working with there in the tutorials. But what I thought I'd do today is show you another example of a differential equation, but this time make it a bit more realistic and provide some of the context from where it might come, and look at various types of solution that it may have. Okay? So I'll just set this to record. Okay. This concerns this ODE that we're going to look at. This is an ODE for a simple model of, say, some spaceship landing gear. Well, spaceship. Bit of grand term spaceship, but some landing gear. So, draw a diagram of this. Now, it won't look much like a spaceship. But we think of having some mass, and this mass is going to land on some kind of planet, and it's going to have some kind of wheel or landing gear attached to it that it's going to land with. But how it's connected to the landing gear is it's connected to the landing gear by two components. One component is a spring. Okay, because when we don't want it to just crash into the planet's surface. So we're going to imagine this thing dropped onto the planet's surface. So we're going to have some spring, which will cushion the impact. But if we just had a spring there, the thing would come down to the surface and just kind of bounce around wildly, perhaps. So to counteract the effect of the spring, we also have what's called some kind of damping mechanism. So I'll explain what these are. So this is sometimes called a damping pot. Damping pot. Okay. So this kind of thing is a spring. And the spring has a kind of resting length. So familiar with it, if you have a spring, you can just put it on the table and leave it there, and it doesn't do anything. Or if it was compressed, it will expand, whatever. Or if it was stretched a bit, it'll retract. But it has some natural resting length, spring. Okay. If x is the displacement of that, of the resting length, then the spring exerts a force on any object attached to the end of it. So if you compress the spring wants to grow again, so it applies a force to lengthen the spring. And if you stretch the spring, well, the spring wants to contract again back to its natural length. So it implies some kind of restoring force. So if x is the displacement of the resting length, Sorry, my making clear there. So if x is the displacement of the resting length, the spring, x could be positive or negative. If x is positive, we're stretching the spring. If x is negative, we're compressing it. Think of this and it's being fixed. The spring exerts a force F, and F is of size, so it's the size of the force exerted by the spring is minus kx. So k is like the coefficient of springiness of the spring. Okay. So depending on whether it's a strong spring or a weak spring, k will be large or small. So k is large, it's a very strong spring. So if you compress it a little bit, you get a large restoring force. Stretch it a bit, you get a large attracting force. Okay, so k is the coefficient of the spring. Then the damping pot, this kind of component. This kind of diagram is meant to evoke, because sometimes these are made of these kind of chambers which will be filled with some kind of fluid, maybe some gas or some liquid, and there's a plunger. And if you try and compress it or pull it apart, it's very hard to do that. It resists being expanded or conversely squashed. Okay? So again, it'll have some kind of resting length, and we can use x to measure the displacement, whether you're trying to stretch it or contract it. So the damping pot, again, resists stretching or compression like a spring, but in a different way. The force that it exerts doesn't depend on the amount that you try to stretch it by or compress it, but the speed at which you try to do it. So if you have a damping pot, you can pull it apart very slowly without too much trouble, because you're pulling it apart and the liquid or gas can flow into or out of this chamber without too much trouble. But if you try and do it very, very quickly, it's very hard. Much larger force to do it quickly. And the same with compressing it. Okay. So the damping pot, again, resists stretching or compression by applying a force. This time the force, so it's negative times x, but it's times x dot, the first derivative of x. Okay? The velocity, so it depends on the velocity at which you're trying to compress it or stretch it. Okay? So it doesn't mind if you try to stretch it or compress it slowly, but if you try to do it quickly, it resists that with a force which is proportional. The B is some kind of coefficient of the damping pot, whether it's very strong or weak. It resisted this coefficient. It's proportional to the speed at which you try and compress it or stretch it. Okay. So where x dot is dx dt. So the spaceship will be dropped. These are the components, an explanation of how the components work. So we'll assume that this landing ship is dropped from a height h. It's just simply dropped onto the planet's surface. Under the influence of gravity, gravitational acceleration g. So we'll keep all these parameters general, so that these parameters will feature in our solution. Well, if that's the case, then the impact velocity, the velocity when it hits the ground after it's fallen through a distance h, the impact velocity of the square root of 2gh. Okay, so the square root of 2gh will be its impact velocity. So suppose we're given values of these coefficients. Suppose we've got a mass of 50 units. The damping coefficient is 180. Spring coefficient, say, is 474.5. These are the figures I'm using. The task here is to investigate the effect of different drop heights. So what's the effect of dropping it from different drop heights? How is it going to react after impact? Okay? So when it's falling, the whole contraption just kind of falls. But when it impacts the surface, then the spring and the damping pot are going to come into play. The spring will absorb, will be like suspension, so it will stop the mass crashing into the planet or coming to an immediate halt. So it will allow the mass to bounce around a bit, and the damping pot will stop it bouncing around too much. It will provide some kind of braking on the bouncing around. Okay? So where does the ODE come from this? We have to explain. So using Newton's third law, that force is mass by acceleration. So this is the mass times x double dot is the acceleration. And we get the ODE we get this differential equation that mx, m times the second derivative, see if the force due to gravity acting on the mass, then you've got the spring force acting on it and the damping force acting on it. Okay, so this is x as a function of t. So s is a function of t, with t equal to 0 being the impact time. So at t equals 0 is the first instant where the wheel touches the planet. That's the first instant it makes contact with the planet. Previous to that, the whole contraption is just falling. So x, sorry, I should have indicated on the thing. Sorry, the way I what x is, x of t is the displacement of the mass away from its resting. Okay. So when this thing is in free fall, the spring will return to its kind of resting length. Okay, so you'll have the mass and the wheel, and they'll just be falling, so there's no net force acting on the thing. So the spring, the spring will be at its rest length. And so once it hits the ground, of course, then the mass will move towards the spring and so on. So we use x to represent this thing. So it's the displacement of m away from its resting length. Okay. So x measured, if x is positive, that means that we're stretching out the contraption. If x is negative, it means we're squashing it down, squashing the mass closer to the wheel. So x is a function of t, t being the impact. And we have some initial values to go along with this, that at the impact time, at the moment of impact, x is 0. So at the moment of impact, the spring is at its resting length. Okay? The spring is at its natural length. And the velocity at impact velocity impact is the square root of 2gh. Okay. That's the rate of change vectors. Okay, so we can solve this using Laplace transforms. Just going through the normal steps. So when you transform the whole equation, you'll have mass times s squared times the transform of x minus s x0 minus x prime 0. And this will equal mg over s, because the transform of the constant mg is going to be mg over s. B minus k times x bar minus b times s x bar minus x0. Okay, so that's what we get when we transform the whole ODE using our transform of derivative properties and transform the constant and so on. So then when you put in the original, or you put in the initial values, and you solve for x bar, we get the solution to the transform problem. There's two components to it. There's this first component which doesn't have any h in it. And then this second component over here, which is ms squared plus bs plus k. This is what the solution to the transform problem appears like. Okay, this is still okay. We were given some values of m, b, and k in question, so we'll be able to put those in now. But now the way that the inverse transform of this will work is kind of sensitive to the values of those various parameters. So to make our life easier, and just to display some of the capabilities of it, we'll make use of the computer to do this. So I've prepared a little worksheet here in Sage to take the inverse transforms and to look at the solution. But you can do something very similar in MATLAB. So MATLAB has commands in it for Laplace, for taking the Laplace transform and the inverse Laplace transform. So there's a command Laplace, which is to take the inverse Laplace transform of a function, and I guess it's called Laplace to take the Laplace transform. So you can use MATLAB to take inverse and forward Laplace transforms. So here I am just using the system Sage to do that. Instead, I'll put a link to this worksheet in the comments to the recording. So we can set up the various values that we were given. So we were given a mass of 50, the damping coefficient of 180, and the spring coefficient of 474 odd. We're using gravity here of 9.8. Gravity here of 9.8, so this is an Earth-like planet. Okay, so we feed in these values. This command var sth just gives us symbolic variables st and h. So in the solution, we see we've got this quadratic polynomial ms squared plus bs plus k. So I just define that here. And then this x term 1 is this so x term 1 I define as the inverse transform, you can see there, of m over of m times the square root of 2gh over the quadratic. So this is actually, no, sorry, I was looking at the wrong thing. M times g over s times the quadratic. So that's the inverse transform of this first part here. So that's the first component of the solution, x. So you see I formed m times g over s times the quadratic, and then I take its inverse Laplace transform, specifying the variables s and t. It's just the way the command works. So this is the inverse transform we're looking at. We're back to a function of t. So this is one part of the solution to the ODE. So you can see it's a mixture of cosine and sines, but they're multiplied by this exponential. So this is some kind of oscillation which is going to fade away. Okay, so it's multiplied by an exponential, which is e to the minus times t. So as t increases, that oscillation bit is going to fade away. Then the second term for the solution comes in the inverse transform of this part here. So I've got m times the square root of 2gh divided by the quadratic, and I take its inverse transform. And then x of h is just the sum of those two using linearity. So the sum of the two inverse transforms. So we can have a look at x so you can see, well, let's just have a look at the solution. So the solution here, see, combination of various things, but they're all these sines and cosines, so these oscillation type terms, but they're all multiplied by this exponential e to the minus 9 over 5t, which is this kind of fading away, this kind of transient nature of the solution, that it's going to converge to 0 as t goes to infinity. So you can see the action represents, so here I've done a drop from so x is depending on the height, h. So I've done a drop from 10 meters here. Remember, x is measuring the displacement off the natural length of the spring. So it settles down, after a while, it settles down to a displacement of about -1. So when it's resting on the surface of the planet, the mass squashes down by 1 meter, or 1 unit, whatever, towards the wheel. That's just the weight of the mass being supported by the spring, so it compresses the spring a bit. But you can see that after, once it lands, it squashes down a lot. It squashes down to just over -2.5, and then it bounces back up a bit and returns, and there's another little dip here, which is kind of hard to see. So it bounces down, squashes, returns a little bit, and then there's a little wobble, and then settles down. But having the solution like this, and especially having the solution here as a function of the parameter h, means you can do things like compare different values, or compare the behavior at or drops from different heights. So here, you see I've got a whole range dropping from 0 meters, 0 units, 5 units, 10 units, 100, or 1,000. So I'm going to plot all these together and just color them different colors, so superimposing all these different plots. And let's zoom that up a bit. That just zooms the text. Not sure. So you can see here a range of different behaviors for dropping this thing from different heights. You can see they all end up settling down to the same level of -1 meter. That's just the natural squashing of the spring that the mass of the ship does when it's resting on the surface. So the blue curve was dropping it from a 0 height. Blue was dropping it from a 0 height, then red, then green, then orange. So blue, red, green, orange. So you can see blue, red, green, orange, dropping it from gradually higher heights produces a bigger squashing at the start, and, well, bigger bounce as well before the final settling down to the equilibrium position for the mass. Having it set up in the computer here also makes it convenient to vary some of the other parameters. So for instance, if you took that, so B, remember, was the coefficient of how strong the damping pot was. So if you were to decrease that a lot, say to take that back to 50, so if you decrease the power of the damping, that means the behavior of the spring is going to be more evident. So you'd expect to see a lot more bouncing around after the thing impacts the surface. Okay, so you can run just all the calculations again quickly. And when you plot that solution for dropping from a height of 10, sorry, still zoomed in a lot there. Yeah, so you can see that with a much weaker damping pot, you get a lot more bouncing around, as you'd expect, because the behavior, the influence of the spring is much more stronger in the mechanism. Okay. And you'd see that again also if you plotted all these different ones from different heights, they'd all be bouncing around a lot more until it comes to rest, and the resting equilibrium position should still be the same, still be -1 meter, but they're all doing a lot more bouncing around. And similarly, if you increase the strength of the damping pot a lot, so it was 180, you put it up to 300, we should see much less pronounced oscillation. Yeah, so if you compare that to the original graph, with the coefficient, damping coefficient set at 180, so the thing squash it down, and then it was quite a significant bounce back up before it came back down again to the equilibrium. Whereas here, there's an initial squashing, but then it's just a gradual return to the equilibrium with kind of no real appreciable bounce beyond the equilibrium position again. Okay, so this is just a nice illustration of how we can use the Laplace transform method for solving these ODEs. And when you have it set up with the computer solving it for you, you can, it's a nice illustration of being able to, well, produce the solution as a function of one of the parameters. So our solution x here, which was a function of time, these are functions of time we're getting at, but we're keeping one of the parameters present in the solution, so keeping the height there. Okay, so we can easily get the graphs for different values of that parameter. And it just shows you how you can easily vary the other parameters as well and investigate the effect on the system. Okay, but the key thing here is lying here in the thing here. The thing that enabled us to obtain the solution was this inverse Laplace transform command. Okay. So I wanted to show you that example to kind of end the chapter with, just so we had a nice example of an ODE coming from some kind of semi-realistic context, and just to give you a flavor of some of the more complicated modeling things we can encounter. So just before I leave you then, so I mentioned before the exercises, the end of chapter exercises, and there's a few extra ones. If you want some more exercises on working with the definition of the transform. Okay? So some further exercises. Further exercises for working with the definition of the transform. So, we spent a bit of time proving various properties of the transform in order, well, to give us the tools that we needed for solving certain types of differential equation. So here are just a few extra related ones, which can all be proved using similar techniques. So we'll assume here that we've got some function little f, which has a Laplace transform capital F. Then the first of these properties is, well, what if we take the Laplace transform of f, but this time we rescale the argument of f? We did look at some examples before of translating the argument of f in combination with the Heaviside, and we looked at the effect of what the transform of the resulting function was. Okay, but here you're shifting the argument, and here the results we're asked to prove that this should be a times f of a of s. Okay, so capital F is the Laplace transform of the original function. So shifting or rescaling the argument to f, rescaling it by a factor 1 over a, produces this effect in the transform, is to rescale the argument to the transform by a, and then an additional rescaling the value of the transform by a as well. The other exercise you can try is to take the Laplace transform of a function related to f, but here we're rather than taking the function f itself, we're looking at the integral of f. So we can make a new function which is integrating f from 0 up to a certain point. That's the upper limit of that integral t. So we're just integrating, I've just written it as f of lambda d lambda. So you could use any symbol, whatever, you're just integrating f. But the variable for this new function is t, and that's the upper limit of integration. Okay? So for large values of t, you're integrating a lot of f over a wide range. For small values of t, you're just integrating a little bit, from 0 up to t. But the Laplace transform of this function has a very clear relationship to the transform of the original function f as well. This is just rescaling the transform by 1 over s. And a hint for this, can show this using integration by parts, I think. And a third example, kind of a harder one. It's quite a bit more of an involved exercise of integration, but it doesn't use any techniques. Doesn't use any techniques of integration that you don't have or you haven't already seen. And it starts off with reminding you about something I warned you about. Okay? Remember, the transform is not, we know the transform is linear. You transform a sum of functions, that is just equal to the sum of the transforms. But the transform is not multiplicative. I.e., the transform of the product of two functions, f of t times g of t, this is not equal to f of s times g of s. Capital G being the transform of little g. I warned you that is not the case. But there is a nice way that the product of the transforms relates to the original functions. And that is true. So the products of the transforms, this will be the transform of another function which is related to f and g, where h is the, and it's what's known as the convolution of f and g. So this is this function h, which is defined as follows. It's an integral. It's a sum of products of f and g. It's a kind of curious looking one. So we're integrating this product between 0 and t, and we kind of integrate g forwards. The factor g gets summed up in the forward sense of lambda, from lambda equals 0 all the way to lambda equals t, but f of the factor f gets counted in reverse. Okay? So at the beginning of the integral, lambda is close to 0, so the factor f is close to the value f of t. And you're evaluating at decreasing arguments all the way down until at the end of the integral, lambda is equal to t, and you've got the factor f of 0 in it. So you're multiplying together values of the two functions f and g, but moving in reverse across the interval 0 to t. Okay? So this operation is called the convolution of the two functions, f and g. It gives you this new function h, and the transform, the Laplace transform of this function h, is the product of the transforms of f and g. So it's not the case that the product of the transforms is the Laplace transform of the product, but it's the Laplace transform of the convolution. Okay. And to do this, you know, you have the various integration tools needed for this. So a hint is you'll probably require substitution. Substitution or change of variable. You probably need to use that technique of integration to get to a proof of that problem. Okay, so I thought it'd be good to end the chapter there by giving you some more tasks to do. I don't want to leave you short of tasks. I mean, my intention with all of these is to provide you with loads of stuff to be working on. You know, there's far more there than we can ever cover completely in the tutorials. That's the whole point. I want to leave you with plenty of ammunition to be working with. You will also find, if you're craving more material, if you look at some of these suggested books, you'll also find some more worked examples, another take on some of the theory associated with. So if you look in at the this one at the bottom of the library block, Modern Engineering Mathematics. It's a good book by Glyn James. So if you click through that link, so the library, now there's physical copies of it, hard copies of it in the library, but if you click through the link on Moodle, you'll be able to access the online ebook version of it. And in the relevant chapter there, you'll find lots more worked examples, lots more practice problems on Laplace transforms as well. Okay? So I might leave that there for this afternoon. And so from next week on, then, we'll be looking at that new chapter on Fourier series.